Gravity is a predictable force. If our sun were to suddenly collapse into a black hole of the exact same mass, Earth wouldn't get sucked in. Our planet would simply continue orbiting in the dark, completely unaffected. A black hole concentrates a massive amount of matter into an impossibly tiny space. This creates a gravitational field that stays manageable at a distance, but becomes inescapable as you venture toward the core. As we see in this diagram, there is a strict boundary surrounding Math-Dense core called the event horizon. This is the exact radius where the velocity required to escape the object's gravitational pull surpasses the speed of light. From a distance, a black hole behaves like any other heavy object in space, but crossing that invisible light speed threshold changes the rules of the universe. To understand what happens when you cross that line, we must set up a thought experiment using two different subjects, a stellar mass black hole and a supermassive black hole. A stellar mass black hole is the collapsed core of a dead star. It contains the mass of several suns, all crushed into a sphere no wider than a small city. By contrast, a supermassive black hole is a galactic titan. These objects sit at the centers of galaxies, weigh millions of times more than our sun, and possess event horizons wider than our entire solar system. Intuition suggests that the larger, heavier object should be the more dangerous of the two, that falling into a giant galactic black hole would result in a far more violent destruction. The reality is exactly the opposite. The smaller the black hole, the deadlier the approach. To see why, we must look closely at how extreme gravity interacts with the human body. Let's begin our hypothetical descent toward the small stellar mass black hole. As you approach, you immediately encounter a tidal force. This occurs when the strength of a gravitational pull changes significantly over a very short distance. Observe how a stellar black hole affects a person falling feet first. The gravitational pull on the feet is vastly stronger than on the head. The body accelerates at different rates. The lower half rushes faster, stretching the person vertically, squeezing horizontally. Astrophysicists have a specific technical term for this process, spaghettification. Theoretical physicist Stephen Hawking popularized this exact astronaut scenario to illustrate how severe tidal forces tear matter apart, atom by atom. Around a small black hole, these lethal forces will physically dismantle you long before you reach the darkness of the event horizon. Now, let's reset the experiment and begin our descent toward the supermassive black hole. Because this object is millions of miles across, the gravitational gradient spanning the length of a human body is practically zero. The pull on your head is effectively identical to the pull on your feet. Without that severe difference in gravity, you experience no stretching. You simply drift weightlessly and silently forward through dark space, feeling entirely normal. The actual moment of crossing the supermassive event horizon passes without consequence. There is no physical barrier and no visual alarm as you slip through the mathematical boundary. Yet, even though it felt like nothing, you have crossed the point where escape velocity exceeds the speed of light. From this moment on, no signal or image of you can ever reach the outside world again. The universe's largest behemoths offer a deceptively peaceful crossing, masking the reality that you have entered a space from which you can never return. Inside the supermassive event horizon, you remain physically unharmed. However, the structure of reality has warped around you. Outside a black hole, you can move freely in any direction through space, but you are forced to move in only one direction through time, forward. Inside the event horizon, those mathematical roles swap. As this space-time grid illustrates, the time axis spends entirely inward, directing all possible future paths toward a single central point. Moving toward the center of the black hole is no longer a direction in space you can steer away from. It has become a moment in time you are destined to reach. Surviving the crossing only buys you a one-way trip into the future, falling inevitably toward the deepest mystery in physics. In your final moments, as you travel further forward toward the center, the tidal forces eventually catch up. They will stretch and destroy you exactly as they would have outside a smaller black hole. Your ultimate destination is the singularity, an infinitely dense, one-dimensional point at the absolute center. At the singularity, the equations of Albert Einstein's general relativity break down, returning nonsensical answers of infinite gravity and infinite curvature. To truly understand what lies at this core, we need a theory that successfully unites the physics of gravity with quantum mechanics,